So welcome to the next class. What we're going to be covering today is a continuation of the discussion of the Android interface definition language, and we're going to talk about some of the syntax and supported data types first, and then we're going to go into some more detail about how you implement AIDL interfaces, looking at the internals, what's generated by the AIDL compiler, and then we'll look at some examples illustrating how to use AIDL and the binder for both synchronous and asynchronous communication. So first, let's start by talking about the supported data types. So we're going to discuss the syntax for the Android interface definition language and sort of the way in which it supports various kinds of data types that you define in Java. So AIDL allows application developers to declare their business logic methods using a Java-like syntax. So the key thing here is Java-like. If you know Java interfaces, then understanding AIDL is very straightforward. But be aware, as we'll see in a second, that not everything that you get in a Java interface is going to show up in AIDL. There's a number of restrictions, which are good things to know. So here's a very simple example. This comes out of the Android source code. There's something in there called the Dropbox Manager Service, or the I Dropbox Manager Service, I standing for interface. And as you can see there, you can go ahead and add an entry, which is a Dropbox Manager entry. And you can go ahead and then get the next entry. You can iterate through this thing one thing at a time, getting back the entries that are in a Dropbox entry. So you can imagine that that's probably used internally by Android to allow you to access your Dropbox content from your Android phone, which is a very useful thing to be able to do. So here are things that are similar with the Java interfaces. So if you know Java, then you know that it's possible to define interfaces that have methods that have typed parameters and optionally a return value. You can also have void to not return anything, but it's common to have a return value of some kind as well. So pretty much everything you know about Java interfaces will apply to AIDL, with a few key exceptions. So here are some of the differences. You cannot define any static fields in AIDL interfaces, whereas you can do that in Java interfaces. Any non-primitive parameters, in other words, things that aren't int, float, double, things like that, they have to be defined indicating the direction in which the parameter is being passed. And the three directions are in, which is the default for primitives, and the only way to do it for primitives. And what that says is that the data will be copied from the caller over to the address space of the receiver. So that's what in means. Out means the opposite. It means the data will be copied from the receiver and returned as a so-called out parameter back to the caller. And then finally in-out, which is you pass it in and you get a result back. I looked through all of Android and I could find no examples of where anything in Android used the in-out parameter passing mode in terms of direction. So it's not very common. Most common things are in. There's some things that use out. And it's important to remember to do this because when you start trying to pass data between address spaces, then you want to limit the amount of data that's passed. So when you say in, it only goes with the request. It doesn't go with the response. When you say out, it only comes back with the response and nothing goes over with the request. So that's why they typically do this. And this is also characteristic of other interface definition languages, things like Corba or Microsoft's IDL they use for COM and DCOM and so on. So this is a very common kind of thing to do. Another set of things that are different is that you can have one-way methods. So unlike a regular Java interface where you invoke a method and it basically returns something, which could be void, but the point is that when you invoke that method, it's going to block until the method call is done. Whether it returns anything or not, the caller is blocked for the duration of the call in a normal Java interface. With Android and AIDL, however, you can designate methods as being one-way. And one-way means that you invoke it, it's copied from the caller's address space down into the operating system, and then the call returns right away. It doesn't wait until the call goes over to the receiver side, is turned back into a method call, is processed, and so on. So that means that they're going to return much more quickly. And we're going to use this one-way capability later when we start talking about asynchronous mechanisms and how you can use asynchronous communication in AIDL by using a pair of one-way methods. So one-way methods don't block the caller. Another thing, methods can't throw exceptions, which is kind of an unusual thing, but that's just one of the things that they do. You can't throw the exceptions yourself. They don't propagate those through the call. That's something that's kind of strange. I don't know why they do that. In languages like Corba IDL, you can in fact throw exceptions and they get propagated back. And then another thing that you can't do in AIDL that you can do in regular Java, you can't have interfaces that inherit from other interfaces. So you have to do some other thing in order to be able to make them compose together in some way. There's a number of different primitive operations that are supported as parameters or return values from AIDL or AIDL methods in Android. The typical things you'd expect, right? So bool, array of bool, byte, int, and array of int, long, array of long, character, array of character, float, array of float, double, array of double, etc. Those are all the kinds of things that you can pass back and forth. You can also return character sequences and strings as well. And just poking around in Android for a few minutes just to look and see what was out there, there's something called the interface for the email service. As you can see here, you can create folders, you can delete folders, you can rename folders, and that allows you to pass in basically account IDs and names of things, the account ID being a long, the string being used as the name. So there's some examples of how you're passing primitives around. Very straightforward, not that much different from normal Java programming. You can also pass around lists. So there's this thing called Java util list. And internally it uses the Java util array list as the implementation. The mapping of the IDL list abstraction is this underlying Java list abstraction. And you can support generic lists. Here's an example of an interface that is defined in parts of Android where you can have this thing that will go and look up what network interfaces are available, and you can do this query, and when the query is complete, you get back this list of, you go ahead and get back a list of things that have completed, which tell you what operators are connected to the network. So there's an example where you're getting back a list of something, in this case a list of operator info. So that's how you can use those kinds of things. There's also something called a map, which under the hood maps to the underlying Java hash map. They don't support generic maps, so you have to give it a type, unlike lists, where you can support generic lists. And when I looked through the Android source code, I couldn't find any examples of maps being used. So I guess it's kind of sort of a science fiction-like thing, or maybe it's a map of a fantasy place that doesn't really exist, like the Shire or Mordor or something like that. So they don't really have a lot of use of maps, but they're available if you tend to use them. I think people tend to use parcels and parcelables instead for various things. That's the next topic. So you can actually define your own data types and have them be passable back and forth as parameters or return values from methods defined in AIDL interfaces. And the way that you do this is kind of interesting. So you define your own class, like this is one that I got out of Android for the status bar icons. There's something called a status bar icon, which implements parcelable. And you, as the implementer of that class, are obliged to fill in a number of hook methods, like read from parcel, write to parcel, and so on. And at the appropriate times, as this Android is doing its thing, it'll end up invoking those methods in the stub or in the proxy in order to get the state of the particular instance of this thing, and then pass that back and forth under the hood as a parcel. And you can see down here, here's an example of how we would use this. We would say, here's an interface called iStatusBar, which is actually a real interface in Android. And you can have a parcelable status bar icon that just says, hey, this guy is being defined as a user-defined type with parcelable properties, this read from parcel and write to parcel hook methods that are defined. And then here's a method called setIcon that takes in a status bar icon as a parameter. So it's pretty open-ended. You can go ahead and add these things as you see fit to Android, and it makes it easier for you to define types that can be used with the overall AIDL mechanisms that Android supports. Any questions about that? Yeah?
Why is there no direction for the primitives? So like int index is nothing.
Because in Java, these particular things are going to be passed by value.
Oh, okay.
So you can't get the result back because they don't have, Java doesn't have the same thing you would do in C or C++ where you can take the address of or pass a reference. That's why. So as you can see here, status bar icon is a Java source file. This other thing is an AIDL source file. And so you can make those work together. There's a description that you can find on the Android web page that talks more about how you pass objects, and it goes through and shows you an example of how to do this kind of thing. So to summarize this particular discussion, AIDL, Android Interface Definition Language, is a relatively simple syntax. It's a subset of the full-blown Java interface syntax, and it lets you define interfaces and then define methods that take parameters and return values optionally. As we talked about before, there's a subset of things you can do there. You can't do all the full-blown stuff. The parameters and return values can be any of the supported types we just talked about. And you can even have interface parameters passed. And we'll see this later when we start talking about asynchronous interfaces in AIDL. What you can do is you can essentially create objects that live in a client that are instances or implementations of interfaces, and then you can pass the references to those things as parameters or return values to other AIDL methods. And this gives you the very powerful ability to be able to pass essentially objects using factories or other gang of four style patterns, and the receivers, when they get those interfaces, can then make method calls on them. So you can essentially pass remote object references around and access them from other processes in other parts of the system. And we'll see a bunch of examples of how that works. Basically what you end up doing is you end up creating this AIDL file using your favorite editor. Typically you'd end up using either the IDE editor environment that you have in Eclipse or your own editor that you may choose like Emacs or VI or whatnot. And the thing you always have to remember is that each interface goes into a separate file. So here's a file that has the iDownload interface. Here's a file that has the iDownload callback interface. Those have to be defined in separate files. And that gets a little bit squirrely and confusing at times. You'd like to be able to glom them all together, but they don't support that kind of combination of interfaces. You have to do them one per file. And that means you, as you'll see in a minute when we look at some of the examples, you have to do a little bit of other syntactic sugar to make sure that the files know about each other, that they understand. For example, in this particular case, notice how the iDownload interface uses a reference to the iDownload callback interface. And so we would have to basically import the iDownload callback interface into this file so it would be visible to be usable by the underlying system. And I think they just did this to make it easier to write the compiler. Honestly, there's no need to do it. Other languages give you more powerful ways of being able to deal with multiple interfaces per file. Okay, so that's just a quick overview of essentially the type system that you have with AIDL. And using those basic building blocks, then we can make all kinds of other interesting things. I did a little experiment just for fun. I ran a search through all the Android source code to see how often they use AIDL interfaces, and I found hundreds and hundreds of examples of where it's used in the frameworks. It's used a little bit less over in the apps and providers portion of the packages directory, but it's still used there as well. It's used probably a dozen or so times, but it's used hundreds of times in the main part of Android, which means that you are often accessing stuff as an app developer in Android that is using AIDL in one way or another. So getting to know how it works is useful. All right, the next thing I want to talk about is how you go about actually implementing AIDL interfaces using Eclipse, and then kind of talk about sort of what's going on under the hood. Now, some of what we're going to talk about here is not strictly necessary. You can get a long way in life as an Android developer and not know some of the things I'm going to tell you. But I want to show some of it to you because I think it's interesting to learn how it works. And as I mentioned last time, it's also useful because it helps you appreciate the tedious and error-prone programming you're not doing because it's done for you by having an AIDL compiler. All right, first let's talk about how you use Eclipse. So basically what you do, it's really easy. If you're not using Eclipse, there's a few other steps you may have to do. But if you're using Eclipse, it's really simple. You go ahead and create a bunch of AIDL files. So here's an example where I've got AIDL files that are in my source directory. And you can organize this as you see fit. One common way to do it is you might put your AIDL files in a separate subfolder underneath the source folder. so that you can have the AIDL files separate from the normal Java files. That's just one thing you can do. And so what Eclipse will then do is it'll go ahead and automatically compile every file it finds in the source directory that isn't a .aidl file. And it sticks those files, which are then converted into Java files, in the gen directory. So source and gen are basically peers. They're siblings at the same level of the directory hierarchy of Eclipse, and the way that packages and projects work and so on. And so if you go take a look at, if you very quickly take a look at the gen directory after you plop AIDL files into the source directory, you will discover that the IDL compiler has run and it's created Java files on your behalf. And the Java files contain a bunch of things, and we'll talk about them. One thing they contain is an actual interface, a Java interface that corresponds to your interface, and that's very important for what you're doing. Then they also contain a couple of other things as well. They also contain a stub, which is going to be used by the service that implements this thing, or it doesn't always have to be a service. Whoever the implementer is of the interface will be relating to the stub. And there's also something called a proxy, and that's what the client will be using. Now, when you're dealing with just conventional synchronous communication between activities and services, or services and services, then in that case the proxy is typically used by the activity or the client, and the stub is used by the service. But as we'll see, when we start doing asynchronous calls, the concept of client and service gets flipped around a little bit, and so you actually may have an activity that is also implementing a stub, and that's so it can get callbacks that come back to it from the service, which is invoking one-way methods on callback objects that were passed to it. And we'll talk about that, and I'll show you the examples. That's one reason why I wanted to skip the quiz, so I could cover all that stuff in detail. Okay, and if you take a look at the documentation here, you'll find out lots more information about how AIDL works. Now, there's a lot of different moving parts here, and it helps to break them down by a number of different criteria. So let's kind of do this. Assuming we have an interface like the iDownload interface, then we're going to go ahead and have a couple of different kinds of entities involved. And when you take a look at your implementation, when you take a look at the generated code, you'll see all of these things and how they appear. So I'm just going to give you a high-level view first. So there's some stuff that comes out of Android, out of the box. There's this iBinder interface that's defined as part of Android. There's a binder class, which is defined as part of Android. The binder is typically something that's local, and the iBinder is an interface that allows you to be able to access something whose implementation may in fact be remote, where remote means in a separate process. So those are the things that Android gives you out of the box. They're always available. Then there's certain things that are generated by the AIDL compiler. So the AIDL compiler will generate this stub class that's nested inside of this other interface we're going to talk about later. And then there's also a proxy class which is nested inside the stub for various reasons. And we'll see how those guys get used in a second. And then finally, what you do as an implementer of the service that wants to define this interface, that wants to provide an implementation of this interface, you come along and you inherit from the generated stub, and you override the methods that were defined in the interface so that you give implementations that are meaningful in whatever it is you're trying to do. And it turns out that this particular hierarchy here, the one that goes like this, these are all service-related kinds of things. And then the proxy is something that the client uses. So the client uses the proxy. The other service side, the server side, which might be a service, or it may be a service that's a callback service, those things are inheriting from the binder hierarchy. And there's a real nice tutorial out there that talks about all this stuff. There are lots of great tutorials, by the way, on binder, so in AIDL. So if there's anything you're confused about in my conversation, you might want to take a look, and there's lots more material out there you can take a look at. So let's take a little bit of time and kind of look at what actually is spit out by the AIDL compiler, because it's kind of cool. So you'll see that what happens is that there's this interface that's generated, and that extends this iInterface class, or interface. And then there's a static abstract class called a stub. And as you can see here, it extends the binder, and it also implements your interface. So in our case, that was the iDownload interface, which has the download image method. So there's a class called stub, and it inherits from binder, and it implements the download interface. And then basically this is this thing that's going to be sort of on the implementation side of the house. And then there's a constructor for stub that's going to go ahead and register an instance of this object with the underlying binder framework. So that's how the binder framework knows that you've got an object that needs to be dispatched. It registers it by using this thing called attach interface. There's also another method that's very important. We see this getting used a couple different places, called as interface. And as interface is typically used by the on service connected hook method that gets called back by the Android binder framework and the bound service framework when the onBind method returns. And what that does is it allows you to take a binder object, or an iBinder object, which is what comes back from the server side, the service side, and be able to narrow it or downcast it down to the appropriate underlying interface that we're trying to define here, which in our case would be the iDownload service. And you can see it's got a bunch of gobbledygook code here where it's trying to check to see whether we need to have a proxy made or whether we're the server side, whatnot. And if we need a proxy, which we're going to in this case, it goes ahead and it says new iDownload.stub.proxy obj. And that creates a proxy, and we'll look at the proxy on the next page. Well, two pages from now. In fact, I'll tell you what, let's go look at the proxy real quick, and I'll come back and talk about the other stuff. So here's what the proxy looks like. The proxy is nested inside of the stub. And basically what the proxy does is the proxy is going to stash away the iBinder, and then it's going to use it shortly. And it's going to use it when the client calls the method through the proxy, the method in our case being download image. So when the client calls download image on the proxy, what happens, as you can see here, is it takes in the string, which is the URI, and this code, by the way, is all auto-generated by the AIDL compiler. And as you can see when you look at it, it's pretty low level and nasty. And what it's essentially doing is it's creating a pair of parcels to contain the data that we're going to send over there, and to get the reply back, it's creating these two parcels. And then it's going ahead and it's going to take the URI that we pass in, and it's going to write it as a string into the underscore data parcel. So that what that's basically doing is it's copying the bytes in our URI that is coming from the client side into this parcel, which keeps track of its type and other metadata. And then it goes ahead and it calls this method called transact, and we'll cover that in a second. And what transact does is it says, here's the operation that I want performed. I want to do the transaction download image operation. And here's the data it should work on, which in this case is the string containing the URI. And here's where I want you to put the reply. And we'll see what happens in a second in that method. And then when it's done, when this thing returns, we take the reply and we copy its result as a string into underscore result. And that's what we return as the return value from that particular method. So as I say here, I simplified this ever so much just because I wanted to make sure that you would be able to follow along with what it's doing without getting it too complicated. Here then is the method called in response to the call to transact. So as you can see here, we call download image, that calls mremote, which is the remote binder object or a proxy to it, transact. That ends up calling back in the stub the onTransact method. And you can see what onTransact does is it takes a look at the code, and keep in mind the code is shown over here. Here's the code that was passed in, the transaction download image. And it has a bunch of stuff. I'm just showing the part that's important. It says, if this is the transaction on download image or download image case, then go ahead and read its data string and then invoke an upcall on the actual implementation method that was defined by the user who subclassed this whole thing in the first place. And we'll look at that in a couple slides. That's the actual call that does the actual work. And so it demarshals the parameter and passes it to the callback, and then what it comes back here is a string, and it marshals that up as a string, and then that gets sent back over to the client as the reply. Okay, so any questions about that? So that's basically the set of things that the proxy and stub are doing under the hood to do stuff like register you. So here's, I'll highlight this guy, to go ahead and register these stub instances, these binder objects, so that they can be dispatched ultimately by the binder framework. It has a way of being able to take an iBinder and turning it back into an interface. As part of that process, it may have to create a proxy. The proxy is an object that has a method that has the same name as the receiver, but when it's invoked, it doesn't do the work. It goes ahead and marshals the parameters, calls this transact method to pass them over, and then when it comes back, it takes the return value and then cracks it open and returns it back to something that's expected by the caller. So notice what's going on here is that this is Java land, and this is sort of gobbledygook passing data around, possibly between different languages land, and so this is the linearization stage. So I think I mentioned before that what a proxy does is it converts a method call into a message, and that message is something that represents the information in the method call so that it can be passed over to a receiver, and that receiver doesn't have to be written in the same language, it doesn't run in the same address space, and so on and so forth. So it gives you flexibility to pass information correctly and efficiently across processes. The receiver side, the stub side, gets called back as the objects come up from underneath the binder framework in libbinder, and the onTransact method is called, and that does this stuff, and that ends up ultimately calling the download image method that we have to implement as the people who want to define this service. So let's take a look at that part. So now that we've talked about the generated proxy and the generated stub, let's talk a bit more about what you actually do to use this stuff. Everything I've talked about for the past 10 minutes, you really don't have to know in order to use what I'm talking about, but it's useful to sort of understand the principles. And by the way, if you use other technologies like Corba or Microsoft COM or other things like Enterprise Java Beans, they're doing essentially the same kind of thing. The patterns that they use, which would be stuff like the proxy pattern, the adapter pattern, the broker pattern, and so on, those are all the same patterns. It's just different realizations in different languages, in different middleware frameworks in different ways. OK, so if you take a close look at the generated code by the IDL compiler, you'll see that there's an abstract method called, or a set of abstract methods, one for every method that was defined in the original AIDL interface. So if we have download image, then there's going to be an abstract method called download image here. And we have to implement this. And you either implement it by subclassing from stub or creating an anonymous inner class, or subclassing and then forwarding, however you want to do it. When somebody has to implement download image to do the thing that you actually want to have get done. So here's what you do. You start out by typically creating a private instance of the AIDL generated stub class. And again, there's various ways to do this. The most common way you'll typically see people do it is they'll go ahead and use this format where you make a new anonymous object and you give the implementation here, just like you guys are doing. And that gets created somewhere, either in the onCreate method or it gets created at class scope or whatnot. And you then fill in the implementation of this stuff as you see fit, either implementing it directly or delegating it to somebody else to do the work. And then the final thing you do is you make sure that that object is returned as the result from the onBind method. So that binder, which implements this interface, is going to get returned back to the caller. And we'll see later, think about how this comes back to you. This comes back via the onServiceConnected call. It'll come back as an iBinder, and then you're going to go ahead and say, hey, take this thing and treat it as an interface, which will narrow it down using a proxy to get you back a way to talk to the interface itself. All right, so let's kind of see how all of these pieces actually work end to end, because there's a lot of moving parts, and some of them are pretty easy to understand. Some of them are harder to understand. Not all of them you have to understand, but I'm going to show you how it works sort of end to end to a certain level of detail. So here we have a client. The client's going to go ahead and call download image on the stub.proxy. So we've got this proxy, and it's going to say download image. And as we saw, that's going to convert the parameter and the return result into parcels, and those are going to get used to pass to mremote.transact. And that's going to take the data that goes there, and it's going to be submitted via a lower level mechanism, probably written in native code at some level, that works atop the underlying Linux operating system. And it uses an I/O control, an ioctl, which is basically a way of passing information to the low-level device drivers. The low-level device driver in this particular case, of course, is the binder driver. And that's the guy that knows how to move the data back and forth between sender and receiver. The data comes up on the other side, which causes the thread that's sitting there waiting for the data to unblock from a call to IOCTL from ioctl. And keep in mind, there's a pool of threads, and they just take turns waiting for work to do. And so some thread is chosen. It's turn to run. And it takes the data, which is pretty low level at this point, and it goes ahead and cracks it open, looks inside it, and figures out which binder object is this actually for. And it uses that information that was registered earlier when we called the attach interface method on the stub, or that was called for us by the constructor of the stub. It uses that information to go find the appropriate binder object and call its onTransact hook. And the onTransact hook, as we saw, does the demarshalling of the parameter, and it goes ahead and it invokes the upcall, it's called an upcall, to the download image method on our particular service. So that goes ahead and does its work. Now, I don't show the next set of things, but what will happen is on the way out of that method callback, on the way back from that upcall, the result is taken. So when download image returns a string, the generated stub takes that string, stuffs it back into the parcel that it was sent along with the original call to onTransact, and then it unwinds the whole thing. It goes backwards. So it'll return, everybody unblocks, and we end up ultimately back at the original call site, and the result comes back as a return value from the download image invocation on the proxy itself. So the proxy blocks, it looks just like a regular method call, just like a regular two-way method call, but in fact the processing was done by a different method in a different process for the object that was the target of that invocation. And that's what's commonly known as remote procedure call or remote method call or some variant on that. Okay, any questions about that? So it's a good thing to know how all these things work. By the way, lest you think that this is only limited to things running on the same hardware platform like the device, obviously there's a long history going back to the 70s and 80s of people doing remote procedure call where you span network boundaries. And the abstractions are more or less the same as what we're talking about here. It's just that you can talk to things that are on actually physically different hosts connected by a network. Android's AIDL and binder RPC does not work that way, but the various RPC mechanisms you might use if you were to use, say, web services or other types of middleware built in to on top of the underlying mechanisms, you can use those to talk from an Android device to something else using a remote procedure call as well. There's a very nice article here that gives more information about binders and shows lots of examples and more code you can look at to see how all the various pieces fit together. Something else that's important to talk about in this context is the issue of call semantics. So what are the appropriate call semantics for the AIDL and binder RPC mechanisms? And it turns out there's a couple subtleties here that you need to be aware of. So if you are in the same address space and you invoke an operation through a proxy, what that does is that ends up just being a direct method call to the receiver, which is in the same address space. So if you're calling in the main thread of control, the UI thread, the call will actually be run in the main thread of control. So it's just borrowing, excuse me, it's borrowing the thread of control in order to be able to run the request. So that's just a direct call. Likewise, if the caller is in a separate thread of control, again, the thread will be borrowed. This is what's commonly called a co-location optimization. So it's taking advantage of things when they're co-located in the same address space, and it's removing a lot of overhead, which is great. It's exactly what you want. Conversely, if you invoke operations on objects that run in a separate address space, like another process, then the semantics are slightly different. Rather than just calling it directly, which it can't do because it can't get to the memory in the other process directly, instead what it's going to do is it's going to go ahead and do all the steps that we just talked about to marshal up the data, send it down through the different layers, and it'll pop up the other side. And it'll be run in a thread from a pool of threads. So the key thing to remember there is when you start calling things that are going to run remotely with AIDL and binder RPC, you have to make sure your objects are thread safe, that they've got the proper synchronization. And we'll take a look at some examples of how to do that. And then the return value goes back the other direction. The behavior of one-way methods changes the semantics a bit. The main difference being that when you do a one-way method, it doesn't block the caller all the way until it gets to the other side. In fact, it's kind of a fire and forget model. It just sort of says, okay, I pass it off to the underlying operating system on the client side, and then I return. And that call continues, but I, as the client, am not obliged to wait any longer for the data to occur. So it returns right away, and there is no actual return value. Now, just to be confusing, if you end up doing a one-way call that's co-located in the same address space, then that is actually going to be a two-way call in the sense that the call doesn't return to the caller until the method finishes running. But there will be no return values that come back or out parameters. So these are typically compromises people make just to simplify the implementation and make it work in ways that are going to be optimized. Not always necessarily semantically consistent, but optimal and easy to implement. Okay, so to summarize this particular discussion, AIDL is the interface definition language that we use, and Android uses it to generate code. And this code allows us to be able to have multiple processes communicating back and forth on the same piece of physical hardware, the device. Keep in mind again that there's no reason to be limited to that in general. That's just the way that Android does it. And if you end up talking between processes that run on different processes, or you end up talking between processes on the same machine, then it's going to have to generate the code. The AIDL compiler will have to generate code to do the marshalling and demarshalling. And that was the stuff that we looked at. That's the stuff you don't have to write. The only way you would end up writing code like that is either if you're going to write a parcelable class, in which case you have to fill in the read from message and write to message hook methods, and they would do all those steps. Or if you don't want to use AIDL and you're going to encode the data through some other means, like something that you would, like a parcel that you would use if you were going to use messages and messengers. Let's see. Whoops, oh, that's annoying. Hold on, let me get rid of this. All right, so the interface definition language that's defined by Android is very similar to Java. It's also very similar to Corba and Microsoft IDL and so on. It's a little bit lighter weight. They don't provide all the full-blown bells and whistles that some of these other more powerful things do. And it basically uses these proxies in order to be able to send the values back and forth without having to worry about address space issues. And as I mentioned before, if you do a little searching in Android, you will find lots and lots and lots of examples of AIDL used to pass information around for lots of things. And that's because under the hood, Android is set up to do a lot of communication between different processes. So that can be handled in a way that's very transparent to the applications for the most part, but it allows for much greater flexibility in how the system is configured and how the system is able to be moved around and co-located or remoted without changing the way in which the code is structured. Okay, so any questions about that? So this is probably giving you plenty of information that you can use to implement the next part of your assignment. All right, the last thing I want to talk about here today, we'll just do this as long as it takes and then we'll be done, is basically how to program applications with AIDL. So I've kind of shown you bits and pieces of this stuff. Now we're going to put it all together. We're going to look at some source code. And what we're going to do here is we're going to look both at how to do this for synchronous applications, and we're also going to look at how you could do this for asynchronous applications. And you'll see that it's very similar, but there are some subtle differences. The good news is that once you understand the pattern, it's really, really easy to do all this stuff. And AIDL and the binder RPC mechanism are doing the bulk of the heavy lifting for you. And we're going to kind of do a little comparing and contrasting about messengers versus AIDL at the end of this lecture and get a chance to kind of think about what the pros and cons are. So you might kind of think about that in the back of your head as we do this discussion. Okay, So let's start off. We're going to take a look at a simple application. This application is going to be used to generate some kind of unique key, some kind of unique ID. And we'll see how it's going to work. And so if you had a need to be able to create unique IDs and be able to have them used by various parts of your program, this service might be something that would be worth reusing for various kinds of things. You could use them for authentication tokens or other kinds of stuff. So the way it's going to work, we're going to have a bound service that's going to be hosted in another app. So the service is going to run in a different app from the client, which requires all the stuff we've been talking about. The client's going to need an ID from the service, which is unique. And if you probably have a hard time seeing this, but if you can take a look at the board up there, basically there's a button called Get New ID. And when you click it, it'll give you back this unique ID, which is something called a Universally Unique Identifier, or a UUID. There's other things that go by similar names. There's a Globally Unique Identifier, or a GUID. So UUID or a GUID. It's a way of being able to represent something that will be unique in both time and space. Under the hood, it does this in a variety of different ways. The overall structure of our solution here is somewhat reminiscent of the messenger example we looked at before, especially if you think about the two-way messenger example that we looked at before. The main difference here is that in AIDL, the calls that we're going to look at here are going to be done synchronously. So if you recall the messenger, what you did with the messenger was you basically worked as follows. Remember, in the messenger model, the onBind method on the services side created a binder object and returned it back to the client. The client got this, which by the way was a messenger. It got that through its onServiceConnected hook method. It got that, converted it into a messenger again, and then it used that to be able to send a message to the service. And when the service got the message, which would come in through its event loop via a call to the handle message hook method on the handler, it would then go ahead and do whatever it wanted to do. And optionally, if you had set it up for two-way communication, you could then go ahead and extract a messenger from the message you got and then call send to pass the reply back to the client. The main way that what we're talking about here is different from that, at least at first glance, is that the messenger model is totally asynchronous. And this model, at least for the first cut, is going to be synchronous. So the caller will block while the call runs. That's one difference. And the second difference was, in the messenger model, everything was done in one thread of control. So there was a looper thread that was all running all the processing. In this model, the different requests by the service, by the bound service, are going to be dispatched in separate threads of control. So you have to be able to make these things thread safe. So I should say they're synchronous, statically typed, and thread safe, whereas messages are asynchronous, dynamically typed, and sequential. So those are some of the ways in which it differs. Now, what we're going to do after we talk first about the synchronous version, which is really easy to do but has some quirky downsides, we're then going to show an asynchronous version that is not that much different, but it follows much the same form. Okay, so let's start off by talking about what we do. The first thing we do is we're going to define ourselves an AIDL interface, and it's really simple, as almost always is the case. So we say what package this guy is from, and that's just so it can encode it properly for identifying it later. And then we have an interface that we call key generator, and it's going to have one method called getKey that takes no parameters and returns a string. Now keep in mind under the hood that the string is implemented as a java.lang.string, but at this level of AIDL syntax, we just say string. Okay, and so now let's take a look at all the various steps that are going to be involved here. Now, the first thing we have to assume is that someone has come along and on the server side, as we'll see later when we look at the code, and registered a binder object that knows how to implement this particular kind of operation. And so what will happen then is when we call onStart, that'll call bind service, passing in an intent, which will be used to start up the keygen service, as we're calling it here, if it's not already running. So that'll go ahead and start. And that'll get the onBind call, which will go ahead and grab the binder, the address of this thing, and it'll go ahead and return it. I guess actually if I was really being very precise, I would flip this around because it's actually being implemented by grabbing this guy. All right. And then that guy gets returned as the on-service connected callback hook on our service connection, which, as you recall, was passed in what we called bind service in the first place. That thing uses the as interface method defined on the stub in order to be able to create an interface that corresponds to the binder that we got back, and that gets stuck away and cached in a data member. And then when someone clicks a button to actually run this service, that goes ahead and invokes the getKey method. And as you can see, what that does is that goes ahead and actually that's not quite right either. This guy is animated incorrectly. I'll fix that later. This guy has to be animated so that he comes back when the reply comes back. So we will fiddle with that at a later point. So this guy gets called, passes over the request, the client blocks the entire time, and then when the call is done, it gets sent back to the client, who was basically waiting for the whole thing to happen. Okay, so that's kind of the set of interactions between the various elements that are here. So that's sort of just showing the big picture view. Now, obviously, some other things have to go on for this all to work. So you'll have to take your AIDL file and run it through the AIDL compiler, and Eclipse does that for you automatically. That'll go ahead and generate the various proxies and stubs, which those things get set in there, and other helper methods that are used, like as interface or the constructor for stub or the other stuff that we talked about. And now we can take a look at the source code. So let's take a look first at the source code that handles this synchronously, and then we'll kind of take a step back and look at how to do it asynchronously. So here's our keygen service. Keygen service, as is always the case, is a service. And it goes ahead and it creates a new hash set of UUIDs. So UUIDs are these universally unique IDs. And we store them as a set. And then we're going to go ahead and do the following. So notice this is how we implement this stuff on the receiver side. We are going to go ahead and implement an anonymous instance of keyGenerator.stub called mbinder. So that's the guy that does the heavy lifting of all this stuff. And as you see, he's got a method called getKey, which is actually going to be exposed out to the interface of the keygen service. And when getKey is called, now keep in mind, when getKey is called, what's the context that getKey is called in? When getKey is called, where is it running? It's not running in the client. It's running in the service. Obviously, it's a service. But there's something more important about that. What's the
Whether the thread that called it?
Nope, because this is a remote call. It would be the same thread if it was co-located. So it's running in a special place. I can see this is going to make a good quiz question. It's running in a thread pulled out of the pool of threads that is sitting over there by the binder. Remember, the binder has a pool of threads, and it just picks one, and it says, here, go handle this work. And that thread, if another call, if there were multiple clients that were calling getKey simultaneously, then those calls would be dispatched by different threads of control. So what does that suggest? What happens if you're being called in multiple threads? What do you have to do? What's the reason? If we have, well, keep in mind, what we're going to do here is we're going to go ahead and generate a random UUID and then add it to the set of things that are this unique set. So what would happen if multiple threads of control were to simultaneously try to access this particular set?
We'd have to walk, right?
That's the solution, but what's the problem?
Take it, yeah.
could override each other.
They could, right, you have so-called race conditions. So keep in mind that things like sets in Java are not thread safe. So if you have multiple threads of control that are accessing them simultaneously to check if something's there or to add them, they'll end up scribbling over each other and overwriting the memory. So how do we solve the problem? Well, the way we solve the problem is by creating a synchronized block. So here's a synchronized block where we're going to synchronize on these on this keys. So this is just a typical Java trick of saying this is a synchronized region, and we're going to use keys as the lock because everything has a lock. And so what we do is we go in here. There's only one thread at a time that's in here, and it's going to loop, continually checking to see whether or not we've generated a unique, non-duplicative UUID. And if we get one that's non-duplicative, then we go ahead and we add it to the set, and we release the lock. And on the way out, we return the UUID as a string, and then that gets sent back to the caller. So that's basically what we're doing here. A lot of important things to keep in mind. You have to make sure you do this with synchronized. You got to make sure that you're not going to be having deadlock or race conditions and so on. So there's stylized ways of handling that because you're running in a separate thread of control for each of these threads. And then we end up returning a binder like we always do. That's nothing new there. OK, so any questions about this particular implementation? What is it doing? Why is it doing it the way it's doing, and so on? All right. So here then is the activity. This is the activity that's going to actually make use of this service. There could be other ways of accessing this service as well. This is just one of them. So we've got some local state. We have something that keeps track of the service. We have something that keeps track of whether or not we're bound. We've got all these callback methods: on service connected, on service disconnected. And as you can see here, this is a good example of where we're using this as interface method. So remember, when on service connected gets called back, what it's getting is it's getting this I binder that was returned back to us by the binder framework when onBind was called, which occurs after you call bind service, right? So that comes back to the client-side activity, which is an activity in this case, but it could be a service just as well. And this comes back as a binder. Go ahead and we narrow this. So we say keygenerator.stub.asInterface. And what that'll do is that'll go ahead and create a proxy that we return here that will actually reference the underlying binder object, which is living in another process. So by getting a proxy back on the client side, it's going to allow us to be able to invoke the download image method later in order to get access to it and do its thing. And then we say we're bound. OK. Now, this actually isn't a proxy. This is actually not a handle. It's a proxy to remote service, to the remote bound service. OK. Here then is the onStart method. Remember, onStart gets called when the activity launches itself into existence. And we're going to do a couple of interesting things here just to be a little different. Someone asked a good question the other day, which I replied to on the mailing list, but you might not have understood the context of the question. So here's an example where when we create the intent, rather than explicitly saying, I want to talk to the keygenservice.class guy, rather than giving him the name of a class file, instead what we're going to do is we're going to say, I want to create an intent who has an action that's the name of this guy. And the name is something you can control, what the name is. And so what this means, as we'll see shortly, is we have to make sure that the manifest file for the service that's going to be started by this thing has an intent filter that is going to basically key off of its name. And it's going to use this in order to be able to limit the number of people who can start it. You have to be able to know its name in order to talk to it. We then go ahead and create an intent called bind service. Bind service, as you can see, goes ahead and starts things off. As that proceeds, that'll end up doing these callback methods because those things get triggered when bind service completes. Here then is actually the interesting part, right? So this is the part that finally gets to use what we've been doing. So here's the onCreate method. When onCreate is called, as you know, when the activity starts, this guy registers an explicit click handler. It doesn't do it through the the layout file that does it just by registering this callback dynamically. And you can see that the onClick method, which is part of this click handler that we're creating and setting, is going to check when it's called. When you click, when you say, I want to generate a new ID, it goes ahead and checks to see if we're bound. And if we're bound, it goes ahead and says, mservice.getKey. And that's what triggers that two-way call. So it actually invokes the two-way remote call. And that will then go out, and as we saw before, will do all the various things to be dispatched by the service using the binder framework under the hood to keep track of all the different pieces. So that's a two-way blocking call. And so however long that thing takes to run, that call will be blocked. Now, therein lies the rub, right? We're going to talk about that in a second. But obviously, generating a unique key is probably going to take very, very little time. So this is not likely to cause the dreaded application not responding exception. But there could be other situations where you would have longer running things like downloading a file. And so we might not want to block in that case. A couple of the loose ends to tie up here is the manifest file for the service that we've got here. As you can see here, it goes ahead and has an intent filter that says, run this service if you get an intent that matches the name of the service. So you use the name of the service as a filter. And we use that over here, as you saw, in order to be able to create an intent that when bound will cause this service here to be started, because it has an intent filter that matches that particular name. We'll talk a bit more later about intent filters when we talk more about the intent framework in Android, but this is just a kind of a down payment on that later discussion. Any questions about any of that? Yes?
I have a question about the type of service. Yeah, I think it should not be the service. It should be the interface in your slide.
Where are you looking? Here?
No. Go back. Yeah, then that's the type service. The private service.
Yeah?
The second line.
Here? Or here?
Yeah. I think it should be the interface, the type.
Let's see. In this particular wacky, crazy case, what we have here is what we're getting back is the service because of the way we implemented the service. So let's go back up here. So this is the service, and this guy is getting exported out because it's an anonymous type. Yeah, that's a really, really good question, and it's confusing. But this thing is being exposed in a way that makes it work for that. Okay. Any other questions? This is the client-side manifest file. All right. The last thing I want to be able to talk about today is the asynchronous version of all this, which is going to be almost identical to what we had before. The main difference is that in this case, we're going to use AIDL in order to be able to do a pair of one-way asynchronous calls. In contrast, the previous example used a two-way synchronous call. So now we're going to have two one-way calls on different interfaces as opposed to one two-way call on one interface, if that makes sense. This solution is actually a lot closer to the way in which the statically typed, more stylized, and multi-threaded. So what you see here is that it's very similar in spirit to the asynchronous version. In other words, the caller doesn't block waiting for the response to come back. The difference is that it's going to be using static typing as opposed to stuffing things in messages, which are dynamically typed. It's more stylized. In other words, there's a very defined way in which things interact, whereas with messengers and messages, you kind of do whatever the heck you want, and it can become confusing as a result. And it's also multi-threaded, which could be both a pro and a con. All right, so let's start by talking about the way in which we're going to define the interfaces. So we actually define two remote interfaces. And as you can see here, we're going to have two of them. One of them is called key generator callback, And that guy is going to define a one-way method for sending a key from the service back to the activity. And the other one is called key generator. And that has a one-way method that takes a reference to a key generator callback as an in parameter. And so, as you'll see later, the way these things get used is we're going to set them up so they can talk to each other and basically allow us to be able to get asynchrony by having a pair of non-blocking one-way calls. So, and remember, keep in mind, when you invoke a one-way method call, it doesn't block. It returns immediately. So it starts the data on its merry way, and then it comes right back. And that's crucial to understanding what we're about to talk about. OK, so let's take a look at how this is all going to work. And one thing you might notice if you were to go back and compare and contrast this little interaction diagram with the one we looked at before, there's a little bit more stuff going on here. In particular, if you take a look, we have a key generator callback object that we're going to be able to need to use here in order to do the right thing. All right, so we start off by doing our typical bound service trick. That starts the service if it's not running. We go ahead and we get the binder object. As I said before, that should be flipped. Let me flip that guy before I forget and fix him up a little bit. I'll come back and make that look pretty later. And so that goes ahead and gets the binder ref. That comes back as the callback to on service connected. That comes back and assigns it as a proxy to this local data member. And then at that point, when somebody clicks the on click button, or when somebody clicks the button, the on click hook method is dispatched by the Android GUI framework. And that guy calls invoke set callback. I mean, he invokes set callback. And set callback is going to pass over a reference to the key generator callback object, which is residing on the client side. And this is a one-way call. And so this thing dispatches the method. And we'll see what happens here. What happens here could be done various ways. I'm going to have the set callback method create the key, and then it's going to go ahead and invoke the method to send the key back to the client. But it doesn't have to work that way. I could go ahead and I could enqueue this work on a work queue and then come back and process it later. It doesn't matter. I'm just doing this here to make it simple. We'll talk about that more when we look at the implementation. So finally, the call comes back to the client as a callback. Notice that both the server call to set callback and the client call back to set key are both run in separate threads that are not the main thread of control. So they're both running in threads that are coming out of a pool of threads. And that's important to keep in mind when you're looking at the way this differs from messengers. Messengers, everything would be in the main thread. In our model, they're in separate threads. OK, so let's go ahead and take a look at the code here. You can see that the server side is pretty much the same. As I said before, I could do some other tricky things to make it more interesting. What happens here is we go ahead and have the set callback method. Set callback is a one-way call, so it's not going to block the caller. The caller is long gone doing other things by the time this set callback method is run. And it runs in a thread that's taken out of the binder's thread pool. We generate the unique ID as we did before. And then at some point, ... we're going to take that callback and we're going to say callback send key. And of course, that is a one-way call as well. So that one-way call is going to be used to send the data back over to the client. Now, what makes this interesting and much more powerful than the two-way model we looked at before is I don't have to call callback.sendKey in the same context as I got the original request to do the work. I could go ahead and put this thing on a work queue. I could put it in a thread pool. I could defer it till much later. I could make it run by a timer. Lots of things I could do. And at some point, it'll run. And so you give yourself a lot more flexibility because you're being able to make these calls much more asynchronous in terms of time and space than was the case with the two-way method calls, where you had to block both the client and the server thread in order to get the job done and get the result back. Here's the client side. A lot of stuff looks pretty much exactly the same. The place where it differs is, whoops. This should say, it shouldn't say get key. This should say set callback, and it's going to pass in m callback. That's what happens when you cut and paste your example code. So we go ahead, whoops, if bound, do the set callback guy. And that will then go ahead and kick off this call, where it'll do the set callback call. So that'll take place. Notice that when set callback is called, it goes on its merry way. It doesn't block. It doesn't stick around waiting for the call. It just comes right back. The GUI, the user activity, is responsive to any other things that may want to take place at that point. We're not waiting. We're not blocked. We're not synchronously in a request response lockstep mode. And then at some point along the way, when the server service side calls send key on the callback object, that will end up causing this guy to get called back. So this guy's going to run in a thread from the activity binders thread pool. And when he gets called back, he's going to go ahead and make a new runnable. Because remember, this guy's running in a separate thread now. He's not running in the main UI thread. He's running in a binder pool thread. He's going to go ahead and create a new runnable, give it a run method, which is going to go ahead and output the text when it runs on the UI thread. So you can see it goes ahead and sticks this thing onto the UI thread by this method called run on UI thread. And since send key is a one-way, it doesn't block the caller. So the server thread is released immediately once it does send key. The client thread is done, so everything is much more asynchronous. Okay, so to sort of summarize everything, the AIDL implements the broker pattern using other patterns like proxy and adapter and activator to do its thing. In contrast, the messenger stuff we looked at implements command processor pattern and activator as well. But there are different patterns used for different purposes with different pros and cons. If you want to do complex things where you have interfaces with lots of methods, with lots of types, you probably want to use AIDL because it's very easy to tell what your interfaces look like. They're strongly typed. You can understand what they're doing. The compiler generates all the code for you. The AIDL compiler generates all the code to be able to do the marshalling and the demarshalling and so on. Likewise, when you use AIDL, the calls by default are two-way synchronous, and the service runs in a multi-threaded mode. If you need to use asynchrony, then you would go ahead and support the callback model that we just talked about. If you want to do simple things, if you're just passing over a string or something else, then using the command pattern, using messengers may work perfectly well for you. It's not as scalable, but it's pretty simple. You don't have to understand AIDL. You don't have to write a separate file. Moreover, everything is serialized and non-threaded and stuff like that. So that may simplify some things too. For many apps, you don't need multi-threading. Multi-threading is overkill. With AIDL, you kind of get multi-threading as a consequence of using it. So be prepared for that. So using messengers may be simpler in many cases, and if you can get by with that, then that's probably the right thing to do. However, if you need to run things multi-threaded for whatever reason, then you probably want to use AIDL. Or you want to write your own threading pool mechanism like you guys did for the latest programming assignment number 3. You may want to use something like that, where you spawn up your own pool of threads. Now, I want to cover just quickly the whole issue of asynchrony versus non-asynchrony with AIDL. Does anybody want to compare and contrast the pros and cons of synchronous-based approaches to AIDL versus asynchronous-based approaches to AIDL? What are the good and bad of those approaches? Patrick.
With asynchronous, you have to deal with issues, sort of side effects of threading.
On the activity as well as the service. That's right. So if you start doing asynchronous stuff, you're getting callbacks that are going to be run in separate threads of control. Now, as you saw, it's not that hard to do by just taking the result and throwing it back on the main thread, but you have to remember that. So that's one thing. What other things? So that's a con of asynchrony. What's a pro of asynchrony?
Accidentally block the UI thread.
You're not going to end up accidentally blocking the UI thread if the service that you call happens to run for an unanticipatedly long amount of time. And so that's probably the #1 reason why asynchrony is the right thing to do. In fact, if it was up to me, I would encourage people to consider always using asynchronous AIDL. So that's the pro part, because it makes everything you do in Android asynchronous and event-driven, as opposed to having almost everything be asynchronous and event-driven, except for communication, which is confusing. So what's the downside? What's the downside to saying everything should go ahead and be asynchronous, aside from multi-threading?
It's more complicated.
You've got to have 2 of everything. For every interface you define, you're going to have 2 interfaces, one of which defines the callback and one of which is past the callback. And once you understand the patterns for doing that, it's not too hard to explain to people why you're doing it. But good luck trying to explain to a garden variety programmer why they suddenly have to double everything that they're doing with something they don't quite understand in the first place. So it takes more thought to understand how to use asynchrony. Another way to put this, a better way to say it, is that the pattern language of asynchronous programming for communication is less widely understood because it doesn't really reflect the typical way we're used to programming communication in non-distributed environments. Now, because normally you make a method call and you wait till it comes back, right? That you don't end up passing callbacks when you make method calls. Having said that, once you're accustomed to event-driven programming, which is what you get with Android, for everything else, in some ways that's more intuitive than having to remember that some things can block for extended periods of time. So the reason why synchronous stuff is good is because it's simple, but the downside is it may block. The reason why asynchronous stuff is good is because it doesn't block, and so it makes things more consistent. The downside is that it's more complicated. So you have to kind of pick and choose, and as you get more comfortable, as you understand these patterns, as you get experience, you will probably do things differently than when you're first starting out and you're just learning. Okay, so I think that is it. And now you're ready to do the next assignment. We've covered everything you need to know. And next class, we'll have a quiz on Monday that will cover all the stuff we covered today and the last 2 times. And we'll also start talking about some of the patterns for things we've been talking about.